All right. Today and tomorrow we're going to look at doing some tutorials, trying to come back on some of the stuff we've seen. So I was kind of going fast up to that point to get to the hash transform so you can do this lab. But because this lab is going to take a few weeks to do anyway, now we can step back a bit and do a few exam type questions. So I think actually these are based on previous year exams. So so today, so this is not on Blackboard yet. I'm going to put that on Blackboard. But yes, so today and tomorrow we're going to look into these guys. Just check the time here. Okay, so this first exercise, so it's based really on the Z transform. So if you look back at your the lecture notes, there will be the transforms. So that would be, I think, part handout 4, the first part of the handout 4, I think. And so anyway, so you have 5 different transfer functions, and we want to find what the so the first question, so you have these 5 ones. The first question is, for each of these filters, classify, no, first, sorry, A, derive the difference equations for the following linear filters, okay? So, first, who remembers what the difference equations is? What is a difference equation? Right, it's a good start. It's we're basically here with the Z transform, but when you look back at the digital domain, so when you look at the sample version, so we just want to write the equations of y at sample nm or xy or whatever you want to call it, is a combination of the input x, or these kind of equations are related the samples y to the sample x. Remember that? So, example, okay, of if you have something like in 1D, say, if you have something like that, for instance. Okay, so that would be your difference equation, okay? All right, so what we want to do here is, so we have the transform of the filters, and we want to see how would you define that as the expressions between the x and the y's, and how you're going to write y, sample y as a function of sample x and so on. Okay? Are you totally lost here again? Yes. No. Right. So let me bring up the handout. This one. So there will be part 1, I believe. All right, so remember this is a definition of your Z transform, and we did this kind of exercise. So we said, okay, this is the definition of my transfer function in the Z domain. And so it turns out it's a FR filter because it's just a polynomial of your Z1 and Z2. And we're looking here at the difference equation. And this is what we do. Okay, so the first step, okay, so I'm going to just go through again that example and you will do the exercise, okay? So that's the definition you have. And you say, well, I know in the Z domain that the convolution is just a multiplication. So I just say the output y is x times the transfer function h, right? That's the starting point, okay? So far, so good, all right? And then you just replace h by the z transform, okay? So you have this polynomial here. And then probably the best way to go around that in this case is just to expand, you know, to just do the, to distribute the multiplication here. So you have x times 4, x times z1 minus 1, and so on. Remember that? And then comes the tricky part. But basically, the way you go around that, okay. Now this is, the things are written on the wrong way. But basically, if you multiply your z transform by z1 to minus 1, then really what you're doing is doing an offset. And it's not an offset of minus 1, it's an offset of plus 1. And the reason why it's plus 1 and not minus 1 is because when you look back at the definition here, remember what happens to the powers. Okay, so that's the raw definition of your z transform. So z transform, the infinite sum of these powers of z, and the power minus n is associated to the sample xn. Okay, so if you're centered in 0, then the power, so you have x0. If you're looking at the sample next to it, so sample 1, then that corresponds to the power z minus 1. Okay, so there's this minus sign, same as in Fourier transform and so on. So, something to remember here, basically when you see that, okay, so the only thing at this point, okay, to come back to the to your discrete domain is you only need to know how you transfer, you know, what is the inverse z transform of this polynomial, this monomial times x, okay? And when you do this, basically the exponents, that would just add a minus 1 to all the exponents in z minus 1, and therefore, but what you're doing here is shifting by plus 1, so there'll be actually this guy here. Have I lost you here? Okay, so I'll just do that again. If you end up with, so if you have something like d to the power of minus d of x of z, in the discrete world, what you're looking at really is looking at the sample of k plus d. All right, so if your current offset looking at is k, sorry, then you need to add, you're doing a shift of plus k corresponds to, in the z domain, to doing this pre-multiplication by z to the power of minus d, okay? Something that you can do back at home. But basically, this is the key for you to be able to recover what the x would be. So coming back on that, so once I have all these offsets, then I'm able to recompute what I just do the inverse z transform, and I get back to this difference equation. Okay? So that's for the FR. So the FR is very simple. You just multiply x by the polynomial of h, or the transfer function. You do that expansion, and then you come back to the x domain. For the IR filters, it's a bit trickier because now you have a ratio of polynomials. So you have, you know, h1 and divided by h2. And so what you do here is it's kind of the same idea, but the only trick difference here is that so you see that, okay, you have this denominator, and that's kind of nasty. But it becomes all simple when you multiply both sides by the denominator, and now you have y times this polynomial equals x, or whatever x times h1. And And then you can go about doing the same thing. And the only difference now is that you're going to have offsets in Y as well. Okay? So basically, you say that to be able to compute the output of a particular Y, you depend on the outputs, the other outputs of Y's at different locations. All right, so that's the, if you want the IR filters, the way to remember it, like you, in a FIR filter, your output, here, only depends, so your output Y only depends on the X, on the inputs. Okay, there's no recursive dependency on what was previously computed or other values. Okay, so just a straightforward mapping. You have a bunch of inputs, and you apply these coefficients. You have a linear combination of these inputs, and then you get your output. Okay. In the IR filter, you have an equation like that, but to compute the output at a particular point, somehow you need to have to know the outputs at different locations as well. So they have a dependency on other previously or future, previous or future computations of your sample. All right. Okay. So, all right. So remember, so if you have the IR filter, the trick here is to multiply both the numerator and denominator by this quantity here, and you're fine. All right. So let's go back to here. Okay, so maybe we'll start with the easiest one of all. I guess that would be this one, so H3. So, okay, first of all, when you see that, is that a FIR or IR filter? Maybe go through them all and just say which one is which, okay? So the first one, H1, is it an IR filter or is it a FIR filter? Who's in favor of FIR filter? Who's in favor of IR filter? All right, correct. It's an AR filter, okay? H2, FR, IR, is it FR? Well, fear. Yeah, okay. So it's not IR, there's no denominator. H3 is FR, H4 is FR, and H5 is IR, okay? So that's quite straightforward here. That was actually question B. So I was asking whether there are an FR. Okay, so in the question here, they actually explicitly say that Z1 corresponds to the horizontal and Z2 corresponds to the vertical coordinates. So, okay, so let's do the easiest one. So H3, so it's 1 minus Z1 minus 1. Okay, so you need to write down what the difference equation is for that particular system. So now remember, you have two coordinates, not only one, as I just mentioned before. All right, if you finish with H3, you can do other ones like H1, for instance, right?
All right, so let's get started with the H3. Maybe I'll zoom out. All right, so you have something like that. So you start with the definition of H3. You start with the
well, the definition of the convolution in the Z transform. So you say y is h times x, and then you plug in your polynomial here, and then you expand. And now that you have expanded your expression, it's quite easy to identify what's going on. So if you take hk as your indices for your samples in the discrete domain, then you have y of hk is x of hk minus, and the z1 minus 1 will become h plus 1 here, okay? Because you're looking at the first dimension. All right. Okay, well, I'm not going to do more of that because that's quite straightforward but painful. So we've done that, okay? So we've done this one as well. So now we ask, the question is, we want to classify the filters as separable and non-separable. And if it's separable, we have to say how we achieve that. So do you remember what separable means in the Z domain? Okay, so separable in the Z domain means that you can express, so basically you can say that if you have h of Z1, Z2, you can say it's h1 of Z1 and times h2 of Z2. Okay, so you can write your, so remember this is one of these rational fractions here. And if you can factorize as in two rational fractions, so one is just expressed in terms of Z1, and the other one is just expressed in terms of Z2. Okay, so you're able to separate the vertical and the horizontal definitions. Okay, so that's kind of how you start. So, right, so X3, is that a separable filter? Bit of a trick question here. So it is because, I mean, you just say there is no term in Z2, so you can say the polynomial for Z2 is just 1, okay? So it is, okay? All right, so let's look at H4. Can you write that down as product of two polynomials? All right, so there's a kind of a trick. So first the question, okay, so is it a product of polynomial? Is it separable? Right, so the simplest way of approaching that is, in this case, okay, there's no denominator, it's just everything's in top, and if you just look at the terms in Z1, okay, then you have 1 plus minus Z1, and all the other terms somehow depends on Z2. So, so you need to try at least that as a possible polynomial, okay? And you look at all the terms in Z2, and then you see that this is just 1 minus Z2 minus 1. All right, so you try that, and you realize that indeed, if you do, so 1 plus Z1 minus 1 times 1 minus Z2 minus 1, that is indeed 1 minus Z2 minus 1
plus Z1 minus 1 minus Z1 minus 1 Z2 minus 1. Okay, which is, I think, correct indeed. Okay. All right, so just what I've done here is just to identify the elements that had no, because I see there's this constant here, so I can say, right, so I know that somehow there will have to be a constant term here, okay? So there will have to be a term here that doesn't involve, a power of 0, basically, okay? So you have no powers of Z1, Z2. So because I look at all the, I know I have 1 times this polynomial, so this polynomial will have to be found exactly in that expression in the polynomial. All right, so see that differently. If you have, if you're looking for something of the form A plus and you have here, say, B0 plus B1, C2, and so on. When you do that, when you multiply, you have A0 times B0 plus, so you have this term here. And so therefore, this expression has to appear somewhere in your, directly in your expansion. Okay. So, and you can do the same. So, I mean, I'll just finish with the H1. Okay, so if you look at H1, so the fact it's on the denominator really doesn't matter. Okay, the question here is like you have H1 of Z1, Z2. I suppose for us now, it'd be kind of write that down as two, well, let's call them Q1 of Z1 and Q2 of Z2. And then, both would be fractions, but I just have to check whether this particular polynomial here is separable or not. And using the same trick, I realize that yes, it is fine, because if you pick up this one to be 1 minus 0.99 Z1 minus 1, and Q2 of Z2 to be 1 over 1 minus 0.9 Z2 minus 1, then then it's all good, right? Because this one is indeed the product of these two guys, all right? Fine, so it's the same story. And if you keep on going, and you'll probably realize that H5 is not 1, okay? So H5 is not 1. Now, H2 is a bit more painful because you have all these terms, but you can do the same. But I would advise you, because all the other ones were kind of nice and small, for H2, probably what you need to do is to have a grid to see especially what the mask would be for that filter. Okay, so we know it's a FIR filter. So really what you have is a mask, just a convolution. And so you can put a grid like that. And this coordinate here would be, for instance, h minus 1, k minus 1. That would be here h plus 1, k plus 1. And so then I can identify what I'm looking at. So Z1 minus 1, Z2 minus 1 corresponds really to this location. So I can say here I have 0.64. Okay, so here I have 0.8 times z1 minus 1. So z1 minus 1 would be here. Okay, so that would be z1 minus 1. That would be d1 plus 1. And that would be z2 minus 1 and z2 plus 1. So I can just fill in all the values here. So I have 0.64 here, 0.64 here, 0.64 here, 0.8, 0.8, 0.8, 0.8, and here in the middle you have 1. All right, so you just identify all the positions in your mask, and at the exam you really have to make sure that because there's a lot of conventions here going on, so well, there's no accepted convention, so you just need to really say which coordinates you're looking at, and do something like that. Just say this coordinate h plus 1, k plus 1, which corresponds to z1 minus 1 and z2 minus 1. And then you can put the mask value, and then you have that. And then when you look at that, you see a massive symmetry going on, okay? And indeed, that is a separable filter. Basically, if you take h1 of z1 to be 0.81, 0.8, and h2, sorry, I just expressed that as a mask. Okay, so this one is a column vector, and this one, this one is a column vector, and this one is a row vector. And if you do this way, then these two are your masks for your filters. Okay, so just write that down again in Z transform. So there will be 0.8 times Z1 minus 1 plus 1 plus 0.8 times Z1 plus 1. And same here, H2 of Z2 is 0.8 of Z1 or Z2 minus 1 plus 1 plus 0.8 of Z2 plus 1. Okay, so this, you expand that in your file. But this, coming back to what it looks like on the grid would be helpful, and we kind of make it clear what's going on. Right, so we've done that. So a video processing system requires a vertical edge strength measurement of an input image. Which of the following filters would you use? Okay, so we're looking at edge measurements, and we're looking at a vertical edge strength measurements. Okay, so all right, so remember, so you have your so if you have your picture, okay, so what we're looking at here, so if you have your picture and there might be a vertical edge. So the vertical edge would be basically, for instance, you're going to have a very dark side of this picture, and here it's very bright, and so that would be your vertical edge. But when you take a slice of that, if you just look at the profile of that slice, you'll get something like that. So high values and go to the dark, okay? Roughly at that point. So even so we're looking at a vertical edge, really the gradient, the changes happening along the x direction, okay? All right, so if you look for a vertical edge, you need something that captures what essentially is a high pass filter in the along the x direction. All right, have I lost you here? Fine. So, okay, so if we're looking, now we're looking at all these filters, we need to identify which one are likely to be high pass filters along the x direction, the first direction, so the horizontal direction.
Yeah, you know what? I don't think we actually have time to do this one. I'll leave that for you as an exercise, okay? I wanted to look at yeah. Sorry. Something more visual and less. Alright. This one will be okay. Right, so okay, so I have a number of filters on the left. So all these guys are filters, and they're defined by the masks. Okay, so you have 1 minus 1 and so on. Okay, so this is the convolution mask. So they are all FR filters, and they're defined by the convolution mask. Okay, and so all right. So I'm looking at what am I doing here? Aha. Right. So I have now this image, or maybe that's impossible for you to see. Alright. That won't work. That'll just be fine. Or I just move this guy this way. Alright, so on the left you have the definition of the masks, and on the right you have the outputs of your system. So what you have here is the original image, okay, and then you have so let's call it output A, clockwise from top right. Okay, so that would be B, C, D, and E. And what we need to do is to associate each of these definitions with the one we're looking at. Okay? All right, so let's start with this one, okay? So P1. So what do we have here? So what kind of filter is that? Is that more kind of a low-pass filter or a high-pass filter? Sorry? High-pass, yeah? Because you usually, if you have a minus sign somewhere, it's not a good start. Okay, it doesn't necessarily mean it's a low pass, but in this case, just you look at the next pixel minus the current one, so you're looking at the gradients of your picture. Okay, and so they will pick up the edges. So they will look at the strong gradient along the x direction. So you're going to pick up what types of edges? The vertical, the horizontal edges. You can pick up the vertical, yeah. So you look at this pixel minus the pixel on the left. So therefore, you're going to pick up any strong changes along the x direction. So therefore, you're going to pick up all the vertical edges. Okay. So if you look here, if there a filter, a picture that only preserves the vertical structure, and that is most likely B. Okay. So I'd say that's B. All right, and you see you have something very similar here, which is this picture D, and you can see that there is a filter, which is P3, that
does the kind of same stuff, except it's along the y-axis. So therefore, I can say that this is D. All right, so yeah, remember this representation, okay, so the mid-gray is 0, okay, so that's the typical definition we have, okay. Okay, so we have two filters with only positive numbers, okay? So what kind of effect do we have? Is it we're more finding edges, or is it more finding a blur? Is it like more, you know, we're going to blur the picture, or we're going to more kind of enhance an edge structure? So who is in favor of blur? All right, it's a blur, okay? So if you see positive numbers, you're going to have some kind of blur effect. So in this case, so let's look at the pictures that have a blur effect. So E has a blur, okay? So you have the original picture, and here's kind of blurred version. And then you have the C as well, which is slightly out of focus from the original image, okay? So the difference between the two is that one is maybe blurrier than the other one, so that would be one aspect. So we'd expect the one that has more blur to have a bigger size of the mask, okay? You need more, you know, to have a bigger blur, you need to have a bigger support for your mask. So, so that's a simple way of looking at it. So you see here you have 1, 2, 3, 4, 5, 6, 7 values, so that's a 7 by 7 mask. And this one has 1, 2, 3, 4, 5. Okay, so it's 5 by 5. So roughly comparable. Now you have to look in details, the magnitude, you know, how much you use the pixels. And here you can see you weight them. Okay, so the weights, and the weights are at maximum at the center, and they're the minimum at the edge. So even so that's a 5 by 5 filter, you see you're really only using most likely only the nearby pixels, so that's more like maybe a 3 by 3 pixels effectively, where this one you're really blurring over really a 7 by 7. So this one looks like a stronger blur than this one. And indeed, you can say that this is E and this is C. Okay. Another way of looking at it, like this blur has uses all the pixels with the same weights, and that means that you will have some kind of little edge effects. And you can see here the transition, even though it's blurred, is not that smooth. Like you don't, it's not the blur you would love to have in a picture. Okay, see some kind of artifacts, kind of a vertical and horizontal structure to it. Whereas here, the blur is more uniform. All right, so, and you're left with the last one, which is therefore A. And that's lucky because A is probably the hardest to find. But basically here, what you're looking at is diagonal structures. Okay, so you're looking at this pixel minus this pixel. So you're looking at along that axis all the edges that are along this diagonal. Okay, and hence you pick up this kind of embossed version of your pattern here. All right. So you have to look at all this stuff. Okay, I mean the usual suspect, like, you know, is it a blur? Okay, and now when I say all the values are, if you have some negative values, it could still be a blur. Okay, it's really only if you only all the values are positive, then you know it's a blur. Okay. All right, so that's it. So we'll do more of that tomorrow. Okay.